Um, all right. Good morning, evening, afternoon, wherever you are. Uh, Today's topic is 96 Boards drone project, and I'm Sarup. I am an applications engineer at Linaro, working with the 96 Boards group, and my day-to-day activities involve making such projects that showcase our partners' boards and their functionality. So the still skipping ahead, but so basically the drone project came across as an idea to create a platform to test different um, 96 boards in a drone environment or a drone like application. And yeah, let's move forward with the slide. So the project goal, starting with the design, was to make it completely out of DIY parts, not to make it super expensive, to try and reuse as much of commonly available building blocks as we can. So that's sort of what we have targeted here. And to so that includes your drone frame, your motors, ESC, propellers, sensors, controller parts, and stuff like that. Expandable design. So the initial design that we have right now involves MCU powered mezzanine. In this case, it's an STM32, and optional expandability. Since it's a mezzanine, you can always attach Cortex A class CE 96 boards, so that would run full on Linux instead of an RTOS, and will do non-real time activities, which we'll cover later on. Open source firmware. For now, it's Zephyr RTOS, and anything else is that's open source is always on the plate. And it's an ever evolving test platform. I never intend this project to really finish, just have different milestones. So the current one is to get it working with Zephyr RTOS and the um, MCU. So in terms of functionality, the main MCU design that we have right now, we aim to provide all digital control using common interfaces like I2C, UART, and CAN. If you look at modern day drones, that you can see all over YouTube, or if you just Google how to make a drone, the stuff that you'll see is mostly controlled via analog sticks, analog radio, and even once the transmission is received on the drones end, pretty much everything else is analog apart from the ESCs, but they also operate in a PWM fashion. So we'll cover that later on as well, and why I don't think that's completely digital. Um, to get rid of all of that and to have a fully digital interface, that would then help us make it fully autonomous. And with our main MCU design, we plan to make the startup sequence fully autonomous. And again, we'll see down the road what the current situation is and how we can improve on that. Then the expanded CE design that comes later down the road will give us fully autonomous flight, 3D mapping using various cameras and sensors, at least 3 or 4 of them to get a 360-degree view, and extremely low latency, high resolution live video stream. Now, this is some place where like we really need to innovate, because currently people use analog video source and transmission, because that provides the least latency, and for FPV purposes that's the best scenario right now. But if we like use really smart compression, some fast FPGAs and custom designs, we might be able to compress the data and transmit it wirelessly while still maintaining the high resolution that a digital source may provide us. um, Moving on, hardware selection, and this is for the drone itself. So the main frame is based on a carbon fiber and wood sort of mixture. It has a wheelbase of 23.5 centimeter. Each arm is around 12.7 centimeter long, and it weighs 110 grams. So pretty light. These are specifically made for FPV racing. And so the main structure is made out of like engineering wood ply, but it's well covered by carbon fiber, so it's actually very stiff and doesn't flex. The motors themselves again are very commonly available, uh, 2300 kV. So for those of you who do not follow the drone scene too much, kV actually means rpm per volt. So with 1 volt, it runs at 2300 rpm, and as you increase it, that just then multiplies. So I've added the dimensions as well. And yeah, so these are pretty heavy motors. Each of them can consume 27.6 amps if they are fully loaded, and a max power output of 408 watts. That's actually more than a lot of gaming PCs if you think about it. So um, we'll see something equally powerful powering it. On the propeller side, yeah, just some simple 4-inch ones, nothing fancy about these. I use tri-blade because they are more stable, um, and dual blades are known to provide faster speeds, but a tri-blade in terms of stability if you're looking for autonomous flights. And a very simple ESC. I'll talk again when I get to the ESC topic. I'll in detail I'll talk about why I didn't choose a more complicated multi-shot or one-shot ESC, on what that even means. Um, but for now, it's just a Simon K 30 amp basic ESC. The way to control them is over PWM with your PWM timings ranging from 1 millisecond to 2 millisecond pulses. And that basically tells how fast it has to spin in that span. Um, Hardware selection in terms of the actual powerhouse, what provides the power for your drone is lipo. This is a smaller one. I would have really liked a larger one. I actually have one sitting around, and the capacity is 1000 mAh. So and even the max continuous discharge is only about 20 amps. As you can see, the drone motors can take around 27. So to get the drone to even lift with that battery, that lipo pack requires around more than 50% throttle. So not the best use case, but that's what I could fit. I'm wondering if there's a better way to turn on the video on my end so I can show off the drone. Uh, let's see.
You don't currently have video enabled, but you
Yeah,
can,
yeah.
yeah.
Not sure what camera that turned on.
Yeah, it looks like it's working. It's from above.
All right, so that's the correct camera I want to be on. So again, that is the drone. These are the rotors. I don't have the blades attached because that would make the drone fly when I'm doing the initial like small demo in a closed space. Um, but yeah, so the lipo pack like fits just snugly inside it. You can barely even see it if at all. um and that is what's powering it. So yeah, just wanted that image to be there for the scale of it. um and let's go back to the slide. Right, so that's the lipo pack. And so a lot of these drones have BECs. They call it battery eliminator circuit, but they are really just step down or step up um, switch mode power supplies. So not really doing the whole AC to DC conversion thing that actual BECs do. But anyways, um, so again, very commonly available stuff. If you just write BEC, you'll see thousands of such units there. And I don't know if that's visible, but here it is. And so yeah, so there's a 5 volt and 12 volt output for your controller boards that you might want to add, which is perfectly good for us. So if I just want to run the microcontroller unit, I can just do that with the 5 volt, and the 12 volts is good for the 96 board spec. So if I want to run the main CE board, that works out as well. The input voltage ranges from 2S to 3S. Now, S in this case donates one single LiPo pack. So 2S would be 2 into 3.2 volts. That's 7.4. Um, and So yeah, 2S to 6S means it can go from 7.4 to, I think it's 18.1 or whatever the top end is. So yeah, so we are just working with a 2S battery pack. So yeah, and yeah, pretty light stuff. Again, standard equipment for modern drones. In terms of sensors, again, very standard out of the box stuff for acceleration and gyro. MPU 6050 does your basic three-axis gyro and accelerometer, and yeah, short enough to just snugly fit in there. Actually, you won't even be able to see because it's quite well hidden in the drone itself. And for the time of flight, we have the ST made VL53L0X, again supported by Zephyr by default. Uses the I2C interface. I'm just using it to detect when it's like off the ground. But for the time being, it is really, really well. It's like down there. I don't know how visible that is, but yeah, there it is. Um, Hardware selection in terms of controller boards. All right, this is going to get interesting. So this is the STM32 sensor mezzanine. Now, I must say, before I show you guys the next slide, I had a very early sample of this thing, and it was sitting for ages, collecting dust and God knows what. So it's based on the STM32F446 MCU, compliant with the 96 boards mezzanine guidelines of it's, as I said, the MCU parts that we're using are the mezzanine so that you can add main boards later on. um, and Yeah, so there's the regular 96 boards, high speed and low speed connectivity. Has a Arduino compatible header on there, but it works at 3.3 volts. So you can attach some sensor shields. And even these days, most shields are 3.3 volts compatible. So that should work fine. Um, and has a bunch of groove connectors for other I2C and UART and CAD and stuff like that. Supports Zephyr RTOS. It has a bunch of integrated MEMS sensors. Um, I was going to use those sensors instead of the ones I just showed you, but as you'll see in the next slide, something happens. Um, on board is the ST-Link debugger, which is like a easy way to just program it without having to go through OpenOCD, which, I mean, depending on your preference, might not be your kind of thing. But and again, so it also has a USB host, but that connects to the high speed header directly onto a 96 boards. So it shows up as a mass storage device. So I think you can like put logs in that place from Zephyr, and then you can access those logs from the CE device if there's a CE device connected down there. But anyway, stuff like that happens, and you end up without a board. So yeah. Uh, so I moved on to another board, the AeroCore 2, and that this board was purposely built for drones. So as you will see, there are a bunch of drone interface. I'll go through them quickly, and a lot of sensors as well. Sadly, none of those sensors were at that time supported in Zephyr, so I did not end up using them. I was kind of short in time with, like, I lost a bunch of time debugging why my last board died. So I just carried on with the sensors I already had. It has CAN bus on board, which will come into play a little bit later. It has a GST-XH connector. The one, I don't know if you can see my mouse, but this white connector here, uh, that is useful to get a voltage reading per cell from your LiPo pack, so you know when it's out of juice. And here you have a sort of a watchdog buzzer, so you need to ping that buzzer continuously through a single GPIO, and that will stay quiet. And if it doesn't receive that signal every 10 seconds or so, it will start beeping, indicated that there is something wrong with the controller, and it's not like just like any other watchdog works. Apart from that, the USB plug here, that says STM console. So in its original firmware, which actually runs PX4, a very very old version of PX4. That's why I decided to get Zephyr on it. But the console port is actually a USB port directly from the SOC, so you can use it as a external storage device or console. So I actually have configured it as an external storage device, so you can have your flash storage attached there, and it will work fine. Um, yeah. So apart from that, there are headers, 8 headers for PWM, 8 headers which originally in PX4 firmware were used for, so the 8 headers for PWM out, and there were headers that were used for PWM in, to take control in from the analog receiver that's usually used on the drones, and so that you can use those big fat drone controllers. And then you have a bunch of communication header, including multiple I2C and UARTs and SPI. And then there's like a SPI bus that like switches SPI switch that connects to multiple SPI devices as well. So yeah, a bunch of drone focused things. So just sort of turned out to be my choice of the board, but I had to do a lot of upstreaming work on it, which at first might not seem as much, but I'll talk about it a bit later. So this is sort of my favorite radio control device from the last few months. This is the HC12. The really neat part about this is that it has great range if you have a proper antenna. I actually have a larger antenna connected to the same HC12 module. Um, it has you can select your baud rate, and it will switch between channels, and it can do channel hopping and bunch of good stuff. But the great stuff is it acts as if there is a physical connection between your drone, or between like two units of the HC12, provided they are on the same baud rate, same channel. And yeah, I think that's about it. And so it just I have my controller, like this is my test controller right now, which is based on an Arduino. And it just as if the Arduino board is directly connected to my STM32 board over a physical UART line. So that way, there's very little configuration to be done, although this can be configured over AT commands. So you can set your baud rate and stuff like that. Moving to support, starting with some of the board support stuff. And I'm going to skim over some of the core software stuff because I can see I just have like 10 minutes almost remaining. So we'll just go through that quickly. For the STM32 sensor mezzanine, the Zephyr support are added by Mani, and I then ended up enabling UART and SPI, which wasn't that big of a deal, but soon after that board ended up burning. So for the Grumsticks AeroCore 2, I ended up doing the full support on Zephyr. So that includes a few bits of the SOC support, since the SOC family was already there. So that was just basically writing DTS. Um, and then I just ended up enabling pretty much any communication standard there was on the board. And yeah, so you can see the link as well. The challenge here was that there were no schematics available because this is designed by Gumsticks, and Gumsticks has their Geppetto design tool, which is basically drag and drop PCB builder. But in that process, they have automated it so much that it never has to generate a schematic. You design your board, and if there are no issues with it, it will directly go into production. And if there are some notes and some issues, then there is some manual interaction with it, but it never really designs a full form schematic. Not only that, it also does the entire BSP generation on its own. So it writes your DTS, your Yocto packages, um, and everything else in between. So most of the IO was guesswork, including older PX4 commits, some PCB tracing, and some trial and error, and just guessing where stuff might be. And Gum6 did provide as much help as they could, but again, even they didn't have the schematics. It's all automated, so it's pretty so it was more laborious than it would have been, difficult per se. So it just took more time. All right, so software design. How everything fits on. So the ESC initialization, and this is the problem I have with PWM controllers. They have only one input. So that means there's no way for the ESC to tell your main MCU any sort of state. It all relays its states in beeping noises that it makes when you power the drone on. And it actually moves the rotors at a very high frequency, and that creates your noise. Um, so it goes into startup, and when you have it at the lowest throttle, it's like at the ready state. So you need to set your MCU to have its PWM be all the way down to 1 millisecond. And when you start rising it up after it has beeped, um, to indicate that it's ready, then you can um, start, actually giving the motors any power. And then if you have during startup the PWM set at 2 milliseconds, then it actually goes into a setup mode and calibration mode. So it's all very manual, designed for um, your m- how most DIY drones are made, where the controller directly talks to the ESC through the transmitter talks directly to the ESC, and the receiver just converts the different signals on like 8 channels to 8 separate PWM signals, and that controls everything. Um, there's a lot of the times, if the drone is well balanced, there is no MCU in between.
Sahaj,
Um,
just to remind you, you've got about 2-3 minutes left, so you'll need to start
oh,
wrapping up soon.
Right. So I don't know if which was quickly reminded of. I don't know if I have the correct firmware available. I try to power it on in a bit. And if there are any questions, do let me know. So let's skip that because you can read that in the slides. I hope that will be posted. But I just wanted to go through quickly through the future plans and commitments. I really want to just remove PWM, and I've been looking into UAV CAN spec, and that has looked quite promising. And so hopefully in the next design of this thing, we have some UAV CAN motors that can give their state back to the MCU. Uh, Add GPS control, so a bit more robust drone firmware instead of me just doing everything manually over Zephyr. So something like PX4, and then adding a full CE board on there. So I think, yeah, let's take questions if there are any.
Great. Thank you, Sahaj. And so sorry to rush you at the end. It's just you have a few more sessions
Well,
left.
my session was also designed for like a proper connected session, so
Yeah.
it
Well,
was a bit long.
no, thank you for that. And I'm just seeing if there are any. So there are a few comments. Um, So there's a comment saying a network subsystem for FSK is the works upstream. Please reach out to me about H212, which, let's see, that's from Andreas Faber at Susi. And let me see if there are any questions in the YouTube channel. No, there aren't any questions at the moment, but if people have questions after this, what's the best way to reach out to you?
Right.
Details?
So yeah, IRC and my email, which I for some reason put my personal email in there, which was a mistake. So shj.sarup@linaro.org. So
Okay.
I will edit that in the final slide that we share at the end.